Hello everyone and thank you for joining. My name is Abdennour Redjaibia from the Computer Science and Mathematics Laboratory at Sukaras University in Algeria. Today I will present our paper titled From Linguistics to Transformer, an explainability-driven analysis of vague learning style detection in text. In one sentence, we do not just ask whether machine learning models can detect learning styles from text, we ask what these models actually learn when they do it and whether that evidence matches what education theory predicts. As we will see, the answer is surprising. So let me start with the motivation. Massive open online courses serve very large and very diverse audiences, and we know that one size fits all content is one of the factors behind disengagement and dropout. One dimension of learning difference that has received sustained attention is learning styles, which is the preferred way a person perceives and processes information. The most widely applied model in practice is the VAC model, which distinguishes three sensory channels. Visual learners prefer images, diagrams, and spatial understanding. Auditory learners prefer listening, discussion, and verbal explanation. And kinesthetic learners prefer physical activity, touch, and hands-on experience. The usual way to identify a person's preferred style is a self-report questionnaire, and these are unreliable and burdensome. Most of the time, students simply do not complete them. So automatic detection is attractive, and that's the first goal of this work. Now, where is the gap? Three observations. First, the vast majority of automatic learner style detection works on structured behavior logs, navigation patterns, time spent on resource, interaction counts, etc. Second, the rich textual data that learners produce, foreign post, written reflection, open-ended answers, etc., remain largely unexplored as a source of style signals. And this is surprising because large natural language processing has been transformed by pre-trained language models like BERT and Roberta, which excel exactly at this kind of text classification. Third, and most importantly, for us is the few models that do exist are treated as black boxes. Nobody has asked the question at the bottom of the slide: when a model labels a sentence as a visual, what evidence is it actually using, and does that evidence align with the psycholinguistic theory behind VAC? That question is the core of this paper. So we ask three research questions. The first research question is the detection question. How accurately can VAC styles be classified from single sentence of text? The second research question is the explanation question. Which tokens actually drive the prediction for each family of models? And the last research question is the alignment question. Does the evidence the models learn overlap with the sensory vocabulary that VAC theory would predict? Our contribution followed directly. We compare three tiers of models, from fully transparent theory-driven baseline to fine-tuned transformers. We apply shape and line systematically. We introduce a quantitative alignment framework between neural attribution and sensory lexicons, and along the way we uncover a modality asymmetry that to our knowledge has not been reported before. A quick look to the data. We use a publicly available corpus of English sentences annotated with the three VAC labels. After removing invalid labels and duplicates, we have 15,450 sentences. The class distribution is reasonably balanced. As you can see in the chart, visual is the largest class at about 38%, with kinesthetic and auditory both around 31%. So no heavy class imbalance machinery is needed here. We apply a stratified 15-15 split into training, validation, and test sets, and the sentences are short, around 22 words on average, consistently across three classes. Everything I report from now on is measured on the held out test set. Here is the overall design. We train three families of models on exactly the same data. Family 1 is the theory-driven model. We built a sensory lexicon from VAC theory. extract 22 handcrafted features, and train XGBoost on them. The key property is that this model is transparent by construction. It can only use theoretically motivated information, so its performance tells us how far theory alone can go. Family 2 is the classic data-driven baseline. TF-EDF vectors with the 20,000 unigram and bigram features, feeding our 4 standard classifiers. Family 3 is a fine-tuned Roberta transformer. And then the part that makes this paper different, we pass all of them through the same explainability lens. Shape for global token attribution, line for local validation, and an alignment framework that quantifies how much of the learned evidence falls inside the theoretical lexicons. So let me detail the theory-driven baseline because it plays a special role. We manually curated the 3 sensory lexicons, over 300 terms in total, covering the verbs, adjectives, and nouns that fact theory associates with each modality. For visual, words like observe, bright, shadow. For auditory, whisper, melodic, rhythm. For kinesthetic, grip, smooth, pressure. From these lexicons, we extract 22 features per sentence, raw and normalized counts per modality, subcategory counts for verbs, adjectives, and nouns, dominance ratios between modalities, and few general text statistics such as sentence length and sensory density. An XGBoost classifier is trained on this feature set. The crucial point is this model is interpretable by construction, and it can only exploit information that the theory predicts. So its accuracy is a direct measurement of how much the signal lives inside the theoretical vocabulary. The data-driven side is deliberately standard, so the comparison is fair and reproducible. On the left, TF-EDF baseline 20,000 unigram and bigram features with sublinear terms frequency weighted. Feeding 4 classifier, logistic regression, a linear support vector machine, random forest, and XGBoost. On the right, the transformer. We fine-tuned Roberta base, 125 million parameters with a learning rate of 20 times 10 to the minus 5. Batch size 32. Maximum sequence length is 128. Mixed precision and early stopping on validation macro F1. Training coverages after 7 epoch. Nothing exotic. The interesting part is what comes next. Here is the explainability framework. We apply partition shape on the fine-tuning Roberta across the entire test set, which gives us token level attribution for each class. We aggregate this per token and per class to obtain a global picture of what the model relies on. Lime complements this with local explanation on 5 high-confidence exemplars per class. An independent method, so agreement between the two strengthens our confidence. Then, the alignment framework. This is the methodological contribution. Metric 1 is the lexicon hit rate, with what fraction of the top K-shape tokens fall inside the matching sensory lexicons. Metric 2, the shape mass distribution, how the total attribution mass spreads across the 3 lexicons, giving a 3 by 3 alignment matrix. Metric 3, the disagreement rate, the fraction of correctly classified sentences whose top 5 tokens contain 0 lexicon match at all. Now the results. Starting with classification. On the chart you can see the macro F1 for all 6 models. Every data-driven model from simple logistic regression on TF-IDF to all the way to fine-tuned Roberta converges in very narrow band around 98.6%. TF-EDF XGBoost is marginally the best model, and Roberta reaches a macro area under curve of 0.999. But look at the bottom bar. The theory-driven model, the one restricted to sensory lexicon features, reaches only 72%. That is a 26-point gap. And this gap is itself a finding. 300 term sensory lexicons built exactly as the theory prescribes captures barely 3/4 of the signal that the simple bag of words model can exploit. Where does the linguistic model actually fails? Its confusion concentrates between visual and kinesthetic. These two modalities share to a lot of embodied language, so the lexicon boundaries blur. We can say from all these results that the prediction is essentially solved, even trivially solved. The real question is, what are these models using? This is where shape comes. So what does the model actually look at? For visual and kinesthetic, the picture is intuitive at first glance. Visual predictions are driven by the presence of the characteristic tokens: imagine, notice, envision, watch, sight, pictures, etc. Kinesthetic predictions rely on embodied language, feeling, pressure, hold, grip, so far so consistent with the theory. But notice the dust chips. Tokens like scope and obvious for visual or emotional sensitive, trying and tight for kinesthetic carry strong attribution, and none of them belong to any sensory lexicon. The model has learned that learning style manifests not only in topic, vocabulary, but in framing, in the level of abstraction and in effective coloring. Kinesthetic language, for example, extends into emotional expression well beyond physical movement, and that leaves the third class. What about auditory? This is where the most interesting finding of the paper appears. Here is the token class association matrix, restricted to the strongest tokens. Red cells are positive association, blue cells are negative. Look at the visual column. Strong positive values for scope, notice, view, picture, and the kinesthetic column, strong positive for emotional, feeling, pressure, hold, exactly what you would expect. Presence-based detection. Now look at the middle column. The auditory column is uniformly negative. Every single one of the top tokens from minus 0.5 to minus 0.76. There is no auditory counterpart to imagine or grip. What this means is remarkable. The model detects auditory text by absence of visual and kinesthetic markers, not by the presence of auditory ones. It classifies by exclusion. Why would that be? Our interpretation is that auditory language is more contextually embedded and less lexically distinct. Words like said, told, or heard are so ubiquitous across all text that they carry no discriminative power. So the auditory signal is, in sense, defined negatively. To our knowledge, this asymmetry has not been reported before in learning style detection. So let's quantify the theory model alignment. Two headline numbers. First, only 14.3% of the transformer's top 5 shape for tokens fall inside the matching sensory lexicon. Second, 41.7% of correctly classified sentences have zero lexical match among their top 5 tokens. The model succeeds using evidence entirely outside the theoretical vocabulary. The shape mass matrix per, breaks this down per class. The diagonal is matching lexicon. Visual aligns strongly. 79% of its attribution mass lands on its own lexicon. Kinesthetic is moderate at 57%, but auditory allocates only 22% to its own lexicon, and nearly half of its mass, 49.7%, falls on the visual lexicon. Because its signal is the negation of visual markers, this confirms with the second independent measurement the exclusion-based detection strategy we saw on the previous slide. A brief but important validation step. Shape is a masking-based approximation. So we across-check it with line, a completely independent explanation method on 5 high-confidence examples per class. The local explanation reproduces the global picture. Visual sentence highlights words like clarity and clear. Auditory sentence shows tone and symphonic. Kinesthetic sentences rely on grip, movement, and pushing, and the auditory asymmetry appears in rhyme as well. Two independent methods telling one consistent story that substantially strengthens our confidence in these patterns. What are the practical takeaways? 3 points. First, prediction is cheap, but insights is not. Since the simple TF EDF models are already hit with accuracy ceiling, there is no accuracy argument for transformers here. Their value is as explanation targets, as instruments for understanding how style is expressed in language. Second, sensory lexicons are incomplete. With only 14% alignment, the way learning styles manifest in text goes far beyond sensory vocabulary into framing, abstraction levels, and effective coloring. That is a message back to the theory. If vague preferences are real in text, the current theoretical vocabulary does not capture how. Third, auditory needs its own strategy. If a modality is detected only by the absence of the other markers, then uniform detection pipeline effectively treats auditory learners as a residual class. Adaptive system should be designed with asymmetry in mind, different detection threshold, and possibly different adoption logic for auditory content. Of course, some honest imitation. The dataset consists of isolated sentences rather than authentic educational discourse. Real forum posts or essays will be noisier. The near ceiling accuracy across even simple models suggests the dataset construction embedded strong lexical cues. So absolute accuracy numbers should be read with care, which is precisely why our focus is on the explanation, not the accuracy. Our lexicons are manually curated and may be incomplete, and shape itself is a masking based approximation. Finally, generalization to other corpora, other languages, and other learning styles framework remains an open question. To conclude, this paper reframes learning style detection from classification problem to an explanation problem. Three takeaways. First, data-driven models exploit patterns that exceed sensory vocabulary by a 26-point margin, so accuracy alone tells us very little about what is being learned. Second, the theory model alignment is weak. Only 14% of the model's strongest evidence matches theoretical lexicons, and 42% of correct predictions use none of it at all. Third, the auditory exclusion effect. The auditory text is recognized by the absence of the visual and kinesthetic markers as an asymmetry that adaptive learning system should explicitly account for. For future work, we plan to extend the analysis to multilingual corpora, which is the particularly relevant in our own context, and to integrate these vague signals into mock dropout prediction pipelines, connecting this work to the broader goal of my dissertation. Thank you very much for your attention. I'm happy to take questions and to discuss.